everyone. So we are continuing our conversation about limits. And today what we're looking at is how to calculate limits algebraically. And so what that means is we're going to be able to calculate limits without relying on graphs and tables. And that tends to happen in situations where we don't have access to a calculator. So we're going to kind of work under the assumption that these would all be no calculator questions. Because the idea is, how could we find the limit without having a visual, okay? And so the good news is, a lot of the times this is easy, okay? Because if you have a nice continuous function, so that's what I'm going to kind of draw here. Okay, if I have a nice continuous function like this one, and I'm looking for a limit as x approaches, I don't know, whatever this x number might be, I should be able to find that limit by just taking this x value and plugging it into the function, okay? So that's what this first option is talking about, is that when things work nicely, when things work the way they're supposed to, I should be able to just take the value that I'm trying to find the limit for, like as x is approaching whatever number, and plug that into the function and get my answer. Now, when that doesn't work, it usually indicates there's some kind of discontinuity. So maybe there's a hole in the graph, or an asymptote, or a break in the graph, something like that. And that's when we're going to run into trouble. That's when these two things are going to pop up. But I'm going to kind of wait to talk about those until we actually encounter it in the examples. So let's just try this first one here. We're taking the limit as x approaches 3 from the right, although if it's a continuous function like this one, it honestly doesn't matter that it's coming in from the right. So I'm going to find this by just taking 3 and plugging it in for x here. So I'm going to say this is 3 squared times 2 minus 3. Well, that's 9 times -1, so my answer should be -9. And so we really like it when they're easy like that, okay? Now in this next one, I can already tell that I am going to run into an issue. And I can tell from the beginning because I know that that -2 is going to give me a 0 down here in the denominator. And that's where these two things come in. Okay, when I run into that as an issue, that's where I run into one of these situations. So let's just see what happens if I plug in here. If I plug in the -2 up on top, I'm going to do some of this math in my head here. So -2 squared is 4. 2 times -2 is -4. And then I have a +4. And on the bottom, I have -2 plus 2. So that works out to be up on the top, that's just equal to 4. And then on the bottom, I have a 0. Okay. This is most definitely an undefined value. When you have a number divided by 0, that is an automatic no-go. Usually what that indicates is an asymptote in the graph. And we're going to verify that in a picture here in just a minute. But for our purposes, this is the end of the road for us. This thing is a limit that does not exist. Okay? That's this situation here. Okay, this limit does not exist. I am going to confirm with a graph here in a minute, although remember a lot of the times you'll be asked to do this without being able to look at a graph, so you have to be confident in your algebra skills. But if you have a number over 0, that is an undefined value, that's going to create an asymptote, and that's a non-existent limit. So this situation tends to surface when we have a number over 0. Okay, let's take a look at that one on a graph real quick so you can just see what I'm talking about here. I've got Desmos at the ready. And so we have x squared plus 2x plus 4. And all of that is being divided by x plus 2. And so you can see this split in the graph. We can see that this graph is not continuous, okay, which is part of the issue. And then I'm just going to throw in the line x equals -2 so we can see where that's at. And that's our asymptote. So I'm just going to switch this real quick so you can see. That's the place where we're taking the limit as x approaches this -2. And that's an asymptote in the graph. One direction is heading to positive infinity, one direction is heading to negative infinity, and so that's why I have a limit that does not exist. Okay, let's take a look back at the next one then. So in the next one I can already tell I've got that same kind of situation going on here. When I plug -3 in, I know I'm going to get a 0, but what happens on top is also important. So let me just show this. On this one, I get negative 3 squared, which is 9, and then plus negative 3 minus 6 over negative 3 plus 3. Okay, so up on the top, that makes a 0, and on the bottom I get a 0. Okay, this thing is the monster under the bed that keeps mathematicians up at night. Okay, mathematicians don't quite know how to deal with this. What is this thing equal to? Is it equal to 0 because it has a 0 on the top? Is it equal to 1 because it's a number divided by itself? Is it undefined because it has a 0 on the bottom? No one really knows. Okay, this thing is what's referred to as being indeterminate. And what indeterminate tells us is that we have more work to do. Okay? Indeterminate means, just like it sounds, we don't know what the correct answer is. There may still be a limit here. This isn't like this one up here where there was definitely an asymptote involved. There may still be a limit even though this function is undefined at negative 3. We've seen lots of those. Okay? So what we have to do now is we need to take this thing and do some algebra magic. Okay, this is where I bust out the, calculus is easy, but algebra is hard saying, because the algebra is what's going to be difficult here. Let's take this thing and think about how we could simplify it. And what's kind of standing out to me is that top looks awfully factorable. So I'm going to kind of move off to the side, and actually the way I've laid this out is not great. We don't have a ton of space here, and I'm just kind of like writing things down as we think about them, but I'll show you in a minute how I would actually write this out. But I'm going to take this expression here and I'm going to factor the top. So x squared plus x minus 6 factors into x plus 3 times x minus 2. You can double check that if you're not sure about that. And on the bottom, I still have an x plus 3. And then what I notice is that my x plus 3's cancel. That is literally me removing a discontinuity. Okay, so this is I'm just going to make a note here that what's happening here is a removable discontinuity. Okay? And so what that means is that I've now reduced this expression down to just x minus 2, and what that allows me to do is take a limit of that expression. So the correct thing to do here would be, and I'm going to kind of rewrite this down here. Again, I didn't leave you a ton of space. But I'm going to find the limit as x approaches negative 3 of this x minus 2 expression. Because what I just figured out is that this is basically equivalent to x minus 2, except for that one undefined value. Okay, and I'm going to show you what happens on a graph there. So if I do this limit, I can plug the negative 3 in, negative 3 minus 2, and I get an answer of negative 5. And that would be my answer to this question. Okay? So really what I normally do when I'm writing these out is all of this stuff here, I kind of work off to the side. Okay, I don't write it as part of my final answer. For my final answer, I would have this expression, and then I would say, hey, that equals this limit, and then I show like how I'm calculating this limit. So my chain of reasoning is kind of from here down, and all of this is kind of work that I do off on my own. Okay, let's look at this one on a graph. My graph disappeared. Come on back. There we go. Okay. So up top here, I want x squared plus x minus 6. And I'm doing this over x plus 3. Okay. And this time I'm doing it as x approaches negative 3, but I'm going to hide that for just a second. Okay, so when we look at this function, all right, this rational function here, it looks like a straight line. And actually the line that it looks like is just x minus 2. Like if we graphed the line x minus 2, it looks exactly the same as the one in red, right? X minus 2 and the x squared plus x minus 6 over x plus 3 look like the same function, okay? And that's because they simplify. But if I'm looking at this original red function and I'm approaching negative 3, watch what happens. So I'm approaching negative 3, look at my x values, negative 4, negative 3.9, 3.8, 3.7. I'm getting closer to that negative 3. When I get right to negative 3, I'm undefined. There is a hole in the graph. That's what removable discontinuities are, is they are holes in the graph rather than asymptotes. And when there's a hole in the graph, you can still find a limit, which is negative 5. Okay? And if you don't believe me, look at your y values here. As I'm approaching, look at what your y values are doing. Negative 5.2, negative 5.1, negative 5.08, 0.7, 0.6. Okay? It's approaching negative 5 even if you fall in a black hole when you get there. And then same thing's happening here. This y value is quickly approaching negative 5 even though it becomes undefined when I actually hit that x equals negative 3. Okay? But my limit value is still this negative 5 over here. And so that's what I was just able to find algebraically without necessarily relying on a graph. Okay, so just to kind of recap, first order of business is always to just plug the number in and see what happens, okay? And you don't necessarily have to show that step. I mean, sometimes it's helpful on a test or a quiz just to know what you did to get your answer, but this part is not so necessary, okay? And if you're able to just plug it in and get an answer, that's great. If you plug it in and get a number over 0, that's an automatic does not exist because that is an asymptote in your graph. If you get 0 over 0, that's when we're indeterminate, and that usually means there is a limit. You just can't find it by directly plugging in. Those are the hard ones, okay? And so that's this option number 2, and that's where we have to pull out some algebra magic. And I'm going to show you a couple different techniques. We've talked about factoring, okay? But we'll talk about some more as we go on here. This next one should go pretty quick because actually when I plug the 2 in up top, I'm going to kind of write this down here. I'm going to get 2 squared is 4, 6 times 2 is 12, and then plus 9. And this is over 2 minus 2. So this makes a 25 over 0. And so that's an automatic undefined. Okay. And if you try, and I said undefined because the value is undefined, but we would say that the limit does not exist. Okay. If you tried to do the thing that we did up here, so if you tried to factor this, I mean, that's great. We could factor it. This thing would factor into x plus 3 and x plus 3. But you'll notice you don't get anything to cancel out because you can't cancel the bottom here. That's why this one is not removable. And that's why we end up with a limit that doesn't exist. Okay? It's only when it's a removable discontinuity that we can, work harder and find that limit. By the way, I wanted to mention something up here with this 0 over 0 thing, and I kind of said this is not the way I would typically write this. There's a big issue in math with saying things are equal to 0 over 0, because 0 over 0 is not a thing, so we can't ever be equal to it. Furthermore, if I say that this limit is equal to 0 over 0, if I kind of use that in my reasoning here, and then later on I followed this path and said it's equal to negative 5, then essentially what I'm saying is that this thing is equal to negative 5, and we know that's not true. So we have to be really careful. You'll notice I always go back and cross these things off. That's because we can't actually say that this limit is equal to this thing, because it's not a thing that you can even be equal to. So just a quick notation, thing there. Okay, this next example with the tangent, I think this is a little misplaced. This should actually be in the second half of the notes. Because we haven't talked about any of the trig magic that we're going to be able to do yet. But I do just want to point out that the first step would be to plug the 0 in, okay? And so when we plug the 0 in, we have tangent of 0 over 0. And if you remember your unit circle, tangent of 0 is just 0. So this thing turns into a 0 over 0, and so we know that this thing is indeterminate. Meaning there's probably a limit, but we're going to have to work harder to find it. Okay. However, I haven't taught you yet what you have to do with a situation like that, so we're going to kind of press pause on that one until we get to the second half of the notes, and then we'll come back and talk about that example some more. Okay, so we've gotten really good at factoring. We've done some factoring up above. These last two are kind of like the reverse from factoring. We're going to use a concept called rationalization, and you've done rationalizing before. First thing I would check is, you know, let's plug the number in, and I can tell you, I'm just kind of spoiling the answer here. Both of these are going to come out to be indeterminate. If you put 0 in here, you get 1 minus 1, which is 0 over 0. Down here, 9 minus 9 is 0, and then square root of 9 is 3, so 3 minus 3 is 0. So we get 0 over 0s for both of these. So I'm just going to kind of make a note here that both of these are indeterminate. We kind of need to know that before we start, because you don't want to start diving into all this crazy algebra stuff until you're sure that you have to. Okay, oops, twisted my camera there. So here's how rationalizing works. You're used to rationalizing the denominator, so this one is going to look more normal to you. Up here, I'm actually going to rationalize the numerator, because that's where I see a square root, and that's where I see an opportunity to get some things to cancel out. The best way to do this, and again, I didn't leave myself a ton of space here. I might just kind of box some space off over here for this work. Okay. Best way to do this is to take this expression and kind of write it off to the side, wherever it fits. So right now I'm just recopying exactly what's there. And to rationalize, I'm going to now take this and multiply by what's called the conjugate, that word should sound familiar, of the top. The conjugate is just, I'm going to use this exact same expression, except I'm going to change this sign right here. So now I'm going to multiply by square root of x plus 1 plus 1. And I'm allowed to do that as long as I do the exact same thing on the bottom. So I'm going to multiply by square root of x plus 1 plus 1. And again, that comes from taking the conjugate here. So let's FOIL up on the top. So when I do square root of x plus 1 times square root of x plus 1, what I end up with, so this is my next line here, is just an x plus 1. Because if I multiply two square roots together, they cancel out. Now, follow me down this next path. Square root of x plus 1 times 1 would give me a positive square root of x plus 1. But then my next step will be negative 1 times square root of x plus 1. So I'll have a negative of the exact same thing. Those middle terms are going to cancel out. And that happens anytime you're working with a conjugate. Okay, anytime you have a conjugate pair like this, your middle terms are gone. So I'm not even going to bother with those middle terms. I'm just going to jump straight to the end here and do negative 1 times 1, which is negative 1. Okay? And then this whole top piece, because I have 1 minus 1, is just going to break down to be just a regular x. I still have the bottom to worry about, but my top, all of that, like when I multiplied here, it just became x. On the bottom, because I don't have a conjugate here to work with, I'm not going to mess around with actually multiplying this thing. I'm just going to write these things side by side. So I'm going to kind of, well, it should go here. Okay, I should be filling that in here too. But I'm going to just jump straight to my final step here. Okay, and write it like that. And so right now, I mean, I'm just messing with this thing. I'm just moving this thing around to get it to where I can plug zeros in. If I try to plug zeros in right now, I'm still going to get an indeterminate form. But if you look, I've got an x and an x that can now cancel. And now I can say that this expression is really just equal to 1, because my whole numerator disappeared, over square root of x plus 1 plus 1. So this expression is mostly equivalent to this expression, with the exception that this one is undefined at 0 and this one is not. Okay? And so this right here, where I crossed that off, that was me removing a discontinuity. Okay, that was, again, that was where I'm removing my discontinuity here. So what that allows me to do is now say that this limit is really equal to this limit. The limit as x approaches 0 of that new expression that I just came up with, 1 over square root of x plus 1 plus 1. And now I should be able to just plug a 0 into that. So if I plug a 0 in, I get 1 over square root of 1, because 0 plus 1 is just 1, plus 1. And that's really just 1 over 2. I kind of squeezed it in there, but that would be my final answer for this question. I'm saying that this limit is 1/2. Let's verify. So I don't want you to just believe me. Okay? So my original expression was a square root of x plus 1. By the way, Desmos is a fantastic tool for doing stuff like this. And again, I know you won't have access to it for your AP test, but while you're learning, it's a really nice tool to have. So square root of x plus 1 minus 1, all divided by x. And we this time are just approaching x equals 0, okay, which is here. And we don't really need this x minus 2 anymore. That was from the last problem. Okay, so I'm wandering along this graph, and I'm approaching 0, right? I'm getting closer and closer to 0. Look what's happening to my y values, 0.541, 0.531, okay? Getting awfully, awfully close to 0 here. When I'm right at 0, I'm expecting to fall in a hole, right? I'm undefined. But on either side, if you look at those y values, oops, didn't mean to do that. If you look at those y values, look at how close they are to 0.5, okay? That's where this is heading in both directions, is we're heading toward 0.5 as we approach 0, which is 1/2, okay? So that's why that limit works. Okay, last one is very similar to that. Let's just see here. We're going to, again, do some rationalizing here, and I would move off to the side. I'm going to take my original expression here. This time I'm going to rationalize on the bottom, and I'm just choosing that because that's where my square root is located. So that's where I have something that I can rationalize. So parentheses here, parentheses here. And again, the first thing I would have done, and I kind of did this in my head but didn't write it down, is I would have plugged the 9 in and verified that I truly do have a 0 over 0 thing. I'm going to multiply by the conjugate of the bottom. So square root of x plus 3. And square root of x plus 3. On the top, because these two are not conjugates of each other, I'm not going to bother multiplying them. I'm just going to write x minus 9 times square root of x plus 3. On the bottom, I am going to multiply. So square root of x times square root of x gives me just an x. Because these are conjugates, I'm expecting the next two pieces to cancel each other out. So I have a 3 square root of x and a negative 3 square root of x. Those are going to cancel. And then negative 3 times 3 gives me a minus 9. And once again, right here, those two things are going to cancel. That's my discontinuity disappearing. Okay? And because my discontinuity is disappearing, now I can find my limit, because I'm essentially taking that hole out of my graph. So now I can say that this limit is really equal to this limit of just the square root of x plus 3. Which means now I can throw the 9 in there. And that's just 3 plus 3. So my answer here is 6. Okay, so that's some of the algebraic fun that we're going to have with some of these. Next up, we do need to talk about some trig properties and some trig identities. I'm going to do that in a separate video because this was enough for one day. But if you do have any questions, as always, feel free to reach out. Feel free to ask in class. We're going to try some of these. We're going to practice some of these. And you'll get good at the algebra. You just have to iron out those details. All right, thanks for watching.